How's it going, everybody? All right, so in this one, we are going to be talking about exponential and logarithmic growth models. You will get to use a calculator for this stuff, and eventually, there are going to be things that you just have to memorize for this stuff. But let's go into kind of some things that are just reminders of ideas from the past. So last semester, we did differential equations, right? And in this one, the growth rate of the population is assumed to be directly proportional to that population, derived from the growth model. Find P of t. So first, we would have to do a separation of variables. And k, since I'm just directly proportional, right, that is coming from kind of like Algebra 1 ideas where you're just like multiplying by some number, k. So now if I integrate both sides, this is ln absolute value of p equals kt plus c. At this point, I'm going to want to exponentiate. So the absolute value of p is equal to e to the kt plus c. And now I'm going to need to get rid of the absolute value here. So the way that we can do that is essentially this e to the c. Let me rewrite this just a little bit differently one more time. E to the kt, e to the c. Because this e to the c, this is a constant. This is just a number. E to the c is just a number, right? So if this is just a number, then what I can do is say the absolute value of p, since this needs to be plus or minus to be able to drop that absolute value, then p of t is plus or minus e to the c times e to the kt. And this e to the c, since it just represents a constant, just a number, that plus or minus will come out positive or negative depending on what I find to be in my particular solution. So it will work out however it needs to work out when we get to that point. So really, this is it. P of t equals ce to the kt. You have seen this before, especially if I remind you of the pre-cal one, pe to the rt, right? This is the same exact thing, where p is your initial condition, e is e, just e, right? R is our k, that's our rate, t is time, and a is our final value or our population here. So this is the same thing that we've been doing up to this point. Cool. But we are going to use this formula to kind of help us work through the next few. So find the exponential growth rate of a population. Bacteria where the initial number is 100,000 and the population was observed to double in 3 hours. So I have P of t equals 100,000 e to the kt on the exponential growth model, and then determine the number of bacteria in 1 day. So if I want to find the model, I need to find this value of k such that I can plug in any t and it comes out. So in order to do that, since it doubled in 3 hours, that means I got to 200,000 in 3 hours. So I have 3k up there. So if I divide over that 100,000, this should be 2 equals e to the 3k. And then if I take the natural log of both sides, this is ln of 2 equals 3k. So k is the value of ln of 2 over 3. So when they're looking for this model, then P of t equals 100,000 e to the ln of 2 over 3 t. All right, and that is our model. If I want to find after 1 day, then I do P of 24, since I'm talking about hours. So I have 100,000. So I get 25,600 bacteria. Alrighty. So that is the idea behind these. Same idea with number 3. Really, it's the same whole deal, so I'm not going to waste your time in this video in solving it. This was just more of like a practice problem that I wanted to do in class with everybody. So let me write the answer. You will find k to be ln of 4/15 over 25. So now the other thing here is how many days will elapse before there are no bacteria. So since I cannot find when it equals 0 because it is an exponential function, just like our last one, right? This is a exponential thing. It's never going to be 0. So if this is not possible, what we need to do instead is say, hey, I can find when it's less than 1, because when it's less than 1, then there won't be any left, right? So if you solve for that, then you will be able to work through this. It comes out to be t is greater than 299.4201 days. All right. Moving on. All right, so this one, we can take time to do the general solution, and I'll kind of show you some of the ideas behind it. You're never going to have to do this for us, so I'm not going to take a whole ton of time to do this. But let's see, if I wanted to do this, right, to find the general solution, I would need to do separation of variables first. So I would have 1 over p 13 minus p dp equals 7 dt. And then I would have to integrate. So now on the left-hand side over here, something important to notice is that I can do partial fractions, decomposition, to separate those, right? What we were doing in 8.5. This can get me to 1/13 1 over p plus 1 over 13 minus p dp equals 7t plus c. Right? That one's pretty straightforward. So then if I multiply over the 13, just to make this easier, this will come out as ln absolute value of p minus ln absolute value of 13 minus p equals 91t plus c. Right? This is negative because that p is negative inside there. And from this point, what mathematicians did, this is kind of counterintuitive, but they tried to solve this and combine their natural logs, and that would mean that this is in the denominator. So that when I actually rewrote this in exponential form, I would have to multiply up the 13 minus p. So they said, that kind of sucks. Instead, I want this to be in the denominator, so the way that I can do that is if I multiply everything by -1. Cool. All right, my computer's being weird, so you get this screen. I'm sorry. But what mathematicians did is they multiplied the entire thing by -1. And what that allowed us to do is instead we would have ln absolute value of 13 minus p minus ln absolute value of p equals -91t plus c. I'm just going to leave that plus c because still it is just a constant. So if it needs to come out negative, it will. It'll come out whatever sign it needs to. Then we can combine these and rewrite this in exponential form. Such that if I multiply up the p and add the p over and make this absolute value, this absolute value with the e to the c just a constant. So I'm skipping a lot of steps. Again, this isn't really something that you guys are going to super need to know how to do, or really at all. And then I can divide over the 1 plus ce to the -91t after I've factored out the p. So I end up with 13 over 1 plus ce to the -91t. Find the particular solution if p of 0 is 5. Well, if that's 5, when I put in 0, then I have 13 over 1 plus ce to the 0 will just be c. So this will become 5 plus 5c equals 13. Subtract 5, divide by 5, so c equals 8 over 5. And that is not my particular solution, that is just the value of c. So what I need to do is be lazy and duplicate. Duplicate. All right, so I need to put in that value of c as 8/5. Alrighty. Find the limit as I approach infinity. Well, as I approach infinity, this e to the -infinity might as well be 0 since it's 1 over e to the infinity. So that is 0. So I have 13 over 1, which is just 13. For what value of p is the growth rate a maximum? So it's talking about the growth rate being a maximum. So that is when my derivative of this will be equal to 0. So if I rewrite that, 91p minus 7p squared. Then my second derivative and if I set it equal to 0, that will be 91 over 14 equals p. And what is that? Divided by 7 divided by 7, that is p is 13 over 2, which is interesting because we've seen that number before a few times. So here's the deal, is that given this form, you need to be able to come up with a general solution. So let's go back and see, right? So notice KP and L are kind of our variables there. So here was our general solution, and it came from this. Well, it looks like the 7 got multiplied with the 13 to make that 91, and it's negative. And then the 13 is just the 13. So that would lead me to believe that P of t is L over 1 plus CE to the negative KLT. That is true. That is the case. This is something that you guys need to be able to do. You need to go back and forth between those two forms flawlessly. Okay, the limit as I approach infinity. Well, it was just 13. I saw the 13 up there. I also saw the 13, if my iPad will let me work, as the L value. That is all it is. It is just L. And when it was a maximum, it was 13 over 2, so L over 2. All right, I got to pause and go do a duty, and then I'll redo it. You won't even notice, though. All righty, so let's finish this up. The growth rate of a population of bears, blah, 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 blah. What is the carrying capacity of the bears? So the carrying capacity is just the limit as it goes to infinity. So this is just L. So in this case, it is 100 bears. What is the bear population when the population is growing the fastest? So the growing the fastest when the growth rate is the maximum, right? That is just L over 2, so 50 bears. What is the rate of change of the population when the population is growing the fastest? So the population is growing the fastest when I have 50 bears. What is the rate of change? Well, that is my dp dt. So if I put in dp dt, when my population is 50, that is 0.008 times p times 100 minus p, which will come out to 20 bears per year. Right? Pay attention to units because it is saying T is measured in years, right? And P is our population of bears. And this is the change in population over the change in years. So 20 bears per year. Alrighty. And I think this is the last one. Yes. So one thing to note too is that they may give it to you in the form, let me make sure I get this number right. I can't think right now. Yep. So 0.3p minus 0.0003p squared. And you have to be able to recognize that this is also one of those, the logistic functions. Rewrite it in this form so it's easier to find your L, easier to find your K, and all of that stuff. All right, so let's see. According to the model, what is the carrying capacity? 1,000 moose. What is the moose population when it's growing the fastest? Divide that by 2. That's 500. What is the rate of change when it's growing the fastest? So dp dt when population is 500 moose. Plural is just moose. All right, so plug in 500 and that's 75 moose per boop year. And find P of t. So this is P of t is 1,000 over 1 plus CE to the negative KLT. K is 0.0003. Right, this is our value of K. This is L. So negative 0.3t. And we do need to find that value of c. So now it tells us that they airlifted, they dropped these guys off. So when time was 0, this was at 61 moose. So put in 61 equals 1,000 over 1 plus c, right? And then our e to the 0 will just be 1, so just 1 plus c. C will work out as 939 over 61. So my P of t equation will equal 1,000 over 1 plus 939 over 61, e to the negative 0.3t. All right, what is the estimated population after 10 years? So P of 10, you would have a calculator for this, but it's 566 moose. During what year did it reach 7,000? So you're just trying to find P of t equals, or sorry, 700. 700, that will happen when t is 11.9375. So in 11 years, which is in 1996, after 1985. Right, and it happens in that year because moose population, it happened like incrementally throughout the year. It's not something that just like magically there's 50 more moose this year or something like that. Okay, did the population reach its desired carrying capacity in the 25 years? So P of 25 equals 992. So no, I mean, they did pretty good, right? But it didn't really reach its carrying capacity. So yes, but not really. So no, probably this isn't really something they would ask or I would ask on a free response, but this is a way of looking at they got pretty close, so they did pretty well in that 25-year amount. Okay, hopefully this is helpful. I'll see y'all soon. Bye-bye.